right, so we want to solve a system of differential equations. For example, dx dt is 3x plus 10y, dy dt is minus 2y. And we want to apply these observations, these connections that we've made to linear algebra now. So we kind of know what the solutions generally should look like. We just need to figure out what are the values that R1 and R2 in our solutions need to satisfy. And what we showed through the previous couple of examples is that R1 and R2, the powers in our solutions, they need to be eigenvalues for a matrix of coefficients corresponding to this differential equation. So I'm going to walk through the steps that we would want to apply in general to solve systems of differential equations like this. And then I've got a whole bunch of practice problems at the end of these slides that you can do to practice this technique. So step one is to take this system up here and write it in matrix form. So in matrix form, this would look like x prime, y prime. If I use that prime notation instead of the dx dt notation, is equal to a, which in this case would be 3, 10, 0, and minus 2 times xy. Okay, so that's what we mean when we say the matrix form of the differential equation. Next would be to find the characteristic equation. So to find the characteristic equation, I'll call that P of lambda. That on the previous slide we defined as saying it's going to be the determinant of the matrix that I get from subtracting this scalar lambda from the diagonal terms. So I'm going to subtract the lambda from 3 and a lambda from minus 2. And if we take the determinant of this matrix, then I'm going to take the product of the diagonal terms. So I would get 3 minus lambda times minus 2 minus lambda, and then we would subtract from that the product of the off-diagonal terms, which in this case, just to be complete, would be the 0 times the 10. Okay, but that would wind up being 0. So our characteristic equation, I'll call that P of lambda, is equal to 3 minus lambda times minus 2 minus lambda, and the other term was 0, so we would want to solve when is this characteristic equation equal to 0. This is a pretty easy one to solve. We would get one eigenvalue at 3 and a second eigenvalue at minus 2. So these would be our so-called eigenvalues. And that tells me what the powers for R1 and R2 would be. So for example, at this point, I know that my general solution for x I could write as some arbitrary constant times e to the 3t plus some other arbitrary constant times e to the minus 2t. So that gives us our solution for x. And then we can use this to figure out what the solution is for y. So I ran out of room. I'll do that on the next slide. Okay, so in the previous slide, we found the solution to the system of differential equations over here. dx dt is 3x plus 10y, dy dt is minus 2y. We found the eigenvalues of that matrix of coefficients to be 3 and minus 2. So we know that our solutions for x and y should have things like e to the 3t, e to the minus 2t. And so we can assume that x is equal to c1 e to the 3t plus c2e to the minus 2t. Y is going to have the similar form. We've got different arbitrary constants, c3 and c4, in the solution for y. And these are not arbitrary coefficients. They may depend on the values of c1 and c2 because our two populations, or our two dependent variables, x and y, are interconnected in this situation. So we want to see let's find out what the values for C3 and C4 are by taking our solutions for x and y and plugging them back into the very top equation, dx dt is equal to 3x plus 10y. So if we're going to check the conditions by using the top equation, then we need to figure out what is dx dt. So in order to find the x dt, we would take the derivative of x, which would give us 3c1 times e to the 3t minus 2c2 times e to the minus 2t. And so now, using the equation that we have up here, I'm going to have that dx dt, which is the 3c1 e to the 3t minus 2c2 e to the minus 2t, that needs to equal 3x. So we're going to multiply 3 times x, so that would give me 3c1 e to the 3t plus 3c2 e to the minus 2t. And then we add to that 10y. So I'm going to take 10 and multiply it by the kind of template that we have for the solution for y. So that would give me 10 c3 e to the 3t plus 10 c4 e to the minus 2t. And the goal here is to figure out how do c3 and c4 depend on c1 and c2. So let's group all of the terms that have a e to the 3t in it. So for example, that would be this term over here, this term over here, and this term over here would be all of the e to the 3t terms. And comparing the coefficients, on the left side we've got 3c1, and on the right side we've got a 3c1 plus a 10c3. And the only way that is going to happen is if this coefficient c3 is 0. So that tells me how c3 depends on c1 and c2. In fact, c3 should be 0. And then we can group our our e to the minus 2t terms together. So on the left side we have a minus 2c2, and on the right side we have 3c2 plus 10c4. And now the goal was to solve for c4. So if I bring the 3c2 to the other side, I get minus 5c2 is equal to 10c4, and therefore c4 is equal to minus 1/2 c2. So this tells me that c4 is not totally arbitrary. It depends on the value that we find for c2. So altogether, y would equal 0 plus minus 1/2 e to the minus 2t. So now we've got our general solution for y, we had our general solution for x, and we can see that we have some dependency between the two, since we have the same coefficient c2 appearing in both the solution for x and the solution for y. So let's walk through a bunch of examples that are going to ask us to solve similar systems of linear differential equations.